This is cpe225, lecture 20, and this is going to be a quick review of the hardware concepts that we did in lecture 19. And then we're going to delve into computer architecture, which is primarily terminology and a little bit of symbology. And then it's just typical stuff you need to know if you're going to do anything with computer architecture. Part of the review, remember RISC-V, it was defined by an instruction set. And it's not RTO, it should be RTL. Defines what every instruction does. And essentially the only requirement of the subsequent RISC-V hardware is that the instructions work as stated in the spec. So I think programmers definitely need to be familiar how the instructions are implemented in hardware. Not just familiar, not super versed in it, and I think it makes people better programmers, and it certainly prepares you for cpe315. So computer architecture, we've kicked that term around a lot, and I remember defining it on the first day, but essentially it's the interconnection of the various modules in a digital circuit that you connect it in a certain way, it'll be a computer. And it's really interesting because roughly it's the same for all computers, roughly speaking. So what we want to do is understand what the modules do and what the modules are. So I've been working on a simplified hardware diagram. It shows just the basic control and data connects, and really the biggest considerations here are how the data flows through the module and what data exactly flows through those modules. So this is the high-level computer architecture that we've been looking at. We're just going to step through these modules one by one. So first of all, over here is the top level. Okay, so the top level is the rest of the stuff on the lower level. And the interesting thing about this top level is every single output and input signal listed up there, except maybe the clock, has to do with I/O. So these are processors that are very I/O oriented. They're general purpose. They don't do anything special. They are designed to handle lots of I/O. So that means that it can talk to a lot of external modules. Okay, the next unit is the control unit. And the control unit is interesting because the spec says nothing about a control unit. It's understood that you're going to need a control unit to implement the instructions that appear in the spec. So this control unit is a finite state machine, which is a piece of hardware that controls other hardware. And seriously, what it's going to do is read the opcode part of instructions and then figure out what instruction is being implemented there, and it's going to send out the right control signals, and generally speaking, it's going to make the data flow through this thing in such a way that it implements that instruction. Okay, what you don't see here, since it's not even part of the spec, is these instructions may implement in a number of instructions, and that's why we essentially have a clock sitting there on this thing. It's going to sequence the flow of data through this circuit. And also what's connected to this is the interrupts. This is handles external exceptions, external events and exceptions, and the control unit is going to say, hey, there's an interrupt, and it's going to do the right thing. What exactly that does is pretty much beyond the scope of this class. So the next thing we have here is a register file, and this holds the 32 general purpose registers, and this is actually a special we'll say memory, and we're going to refer to it as a dual port RAM, which doesn't really mean anything. You have to look at it special. The only thing it means is it's just not a normal RAM. And so it's not normal because it has to read two different addresses, which is these two, and then write to another address, all pretty much in the same instruction. So this is definitely a special type of RAM in this thing, and the data you're going to write to this thing could be data from a load instruction, could be the output of a number crunching instruction, could be the output of the ALU there. It could be one of the instructions, the JAL. The jump instructions also include something having to do with the program counter, and lastly All the input goes into the register file. All the output goes out of the register file. So the next thing we want to look at is this immediate generator. The thing about the immediate generator is inside the 32-bit instructions there's field codes, and we need to extend those field codes 32 bits so we can work with them. And so what we're going to do is some of those numbers are sign extended, some of them are 0 extended, most of them are actually sign extended. So what this module is going to do is take the opcode bit part of the instructions, and it ranges from like I think like 10 to 20 bits. I can't really remember. Not a big deal. You could figure it out by looking at the spec. Anyway, it takes those and extends it to 32 bits, which 32 bits are going to be used by other modules. The next thing we have here is the absolute address generator. What it does is converts relative addresses, which are part of the branch and jump instructions, converts those to absolute addresses. The memory only understands absolute addresses, and so I need to convert them into absolute addresses. So the next module is going to be the ALU here. Okay, so the ALU is going to do all the number crunching operations and bit manipulation operations associated with instructions. And typically, it has to do multiple things. It has to handle different operands coming from different places, and that's going to be controlled by these muxes here. The control units, these control signals are connected to the output of the control unit, so it's going to read, the control unit's going to read the opcodes, figure out what the instruction needs to do, and it's going to send out the right control signals on this thing. And yeah, the arithmetic ALU can also be used to do address calculations for the load and store type instructions. The input and output is not really a module, but what we got here is the input's going to come in from the outside world and go into the register file. The output is going to come from the register file and go to the outside world. So both the input and output are associated with an address, which is what we know as the port ID. And I think that's all the interesting stuff we can figure out for the input and output. So next is, we'll say, the program counter. The program counter holds the address of the current instruction being implemented in memory. And does one of two things. It goes to the next instruction, which is normal operation, or it loads one of the absolute addresses associated with the jump and branch instruction. Next module is the memory module. This is written in a special way. This just has one memory, but this memory is going to hold both the instruction data, which is the program data, and also just generic data. And the idea on this thing is that it has an address for the instructions, but this is the instruction address, but it also has an address for the data with various read and write signals as well. But what you notice the difference in this thing is that it has a data input and a data output, and it has an instruction output, but it has no instruction input. The idea here is instruction memory is considered to be read-only. I can only read that memory. And I'm going to say that's it for this thing. And let's see, stepping through this, we stepped all through this. And okay, so this is computer architecture terms. So the idea is if you take a computer organization course, which is what this is, you got to know a certain amount of terms, and the idea is you need to be able to converse with your colleagues. This includes fellow code writers as well as maybe the hardware designers or people who are adding peripherals or something like that. Okay, so first of all, you're writing code, and there's a notion of software versus firmware. Now, whether you're writing software or firmware depends on your target system. Okay, this has nothing to do with whether you're writing machine code or assembly code or a higher level language code. It has to do with the target system. Okay, so if you're writing software, if you're writing code that will run on many different systems, it's going to be referred to as software. Doesn't matter how you write it or what level you write it at, it is software. Firmware is written to run on a specific piece of hardware, namely embedded systems. Now, if you imagine embedded systems, they have specific input and output devices as compared to like your general laptop computer. It typically, they all share the same input and output devices, roughly speaking. So the big difference here is between these two is embedded systems typically are resource limited, and they often have time constraints. You're programming your desktop computer or something like that, or some mainframe computer. They typically don't have resource limitations or time constraints. This idea is things that have to get done. If you don't address it immediately, something breaks. So every computer, as you know, has memory for data or program memory, and it's I'm not going to even pretend to address all these issues here. There's just an incredible number of memory types out there. What you'll see is through the years, there's just always new types of memory appearing out there, and generally the idea is the new memories support new computer systems such that are better or run faster or something like that. Lots of gray area in memory types, as you'll see coming up here. They try to divide it into different things. We'll say number one is going to be levels of memory, and number two is going to be RAM versus ROM. Okay, so as for levels of memory, low-level memory is considered faster, more expensive, and due to those issues, there's relatively not much of it. Okay, higher levels of memory, they're slower and cheaper, and there's going to be more of it. And so the example is low-level memory, fast and expensive. The idea is it takes chip real estate, that's space on the actual IC. It requires more power, and the idea here with more power is that you're going to drain battery life on this thing, or you're going to have to cool it more efficiently on this thing. Okay, some good examples are cache memory. Cache memories are memory that are part of parallelism of processors, not part of this course, but typically you have data instruction caches, and they are very close to the register, and typically using the data and the instructions from those caches, it's going to be faster than just normal operation. The register file for what we're doing is considered faster than the main memory because it is faster not in the semiconductor sense, but in the sense that if I have to take some data and crunch it or something like that, I got to take it from memory using instruction, crunch it using instruction, and then I have to store it back in memory. The idea is it's considered a higher level of memory because it's going to take longer to crunch data that's in memory as opposed to data that's in the register file. So higher levels of memory, they're considered secondary memory levels. They're slower and cheaper, and they're more of it. Examples are hard drives, tape drives, and thumb drives. And the notion is they're pretty slow relative to semiconductor memory on the IC itself. So semiconductor memory, it's for what we're doing, we're going to consider a second level of memory. It is kind of taking over mechanical memory, such as tapes and hard drives. Tape drives I haven't seen one in many years, but hard drives with the spinning disk, they're still out there. Okay, but the idea is semiconductor memories are just becoming more popular as they become cheaper and having larger capacities, etc., etc. There's two types of semiconductor memories that we're going to look at. There's random access memory, which is RAM, and there's read-only memory, which is ROM. Other types, SRAM, DRAM, static RAM, dynamic RAM, they have special issues with them. They have the speed considerations, they have power considerations, stuff way beyond the scope of this course here, but something here is random access memory. The accepted thing here is you can read from it and write to it, so you can read and write it, and it's also volatile, which means when you remove the power, you lose the contents. So read-only memory, generally speaking, you can read from it only, and the issue is it's non-volatile. So when you remove the power, it retains the memory contents. You don't lose it. Okay, so random access is a super important term. What it means is that it can retrieve any piece of data in that memory. It can access, I'm going to make this better, it can access any piece of memory any chunk of memory in that memory device in the same amount of time. So this is different than, we'll say, a tape drive, obviously, but it's also different than a spinning hard drive, because spinning hard drive has a read-write head, which is going to be in different positions at different times, so that the times are going to be different depending on where the read-write head is. Okay, so both of these RAMs, both RAM and ROMs, generally speaking, are random access memory. So in the end, the final word on memory is, generally speaking, RAM is readable and writable, and it's volatile. Okay, ROM is readable, you can't write it, and it's also non-volatile. So the issue here is that there's a lot of gray area, and for example, a thumb drive, which everyone uses, is, yeah, you can write it, but the notion is that I'm usually just reading the thing, and the overlying factor here is the fact that I turn the power off, and I don't lose that memory. Okay, and then so there's the main type of memories. The signals associated with control with working in memory is the data. That's what you're reading or writing, and the address. That's the location you're reading from or writing to, and then there's a bunch of control signals that give you access to the data. Once again, beyond the scope of this course, but important stuff here is the memory word size. Okay, the word in this context is not really defined, but it is defined as, in terms of memory, it's defined as the smallest chunk of data I can read or write from memory. Now, the notion is that, you know, memories hold bits, of course, but generally speaking, most memories, I don't even think I've ever seen a memory where I can read a single bit. Generally, what happens is I read a bit or write a bit, or I read a bit and then grab just the bits I need, you know, typically using some type of masking operation. The other notion of memories here is capacity, and it's generally how many bits the memory can hold. And oftentimes the capacity is written in bit size, which is independent of word size, which is really not fair because, you know, you can't grab a bit at one time. So I'm not sure why you define the memory in terms of bit size. Super important term here is memory bandwidth. This is the rate at which you can access data in the memory. So if you imagine like a semiconductor memory, there's transistors under there running everything. They have capacitors that need charging, all that stuff. So all the memory operations take a finite amount of time. So the length of those access times limit how much data you can get or you can access in a memory in a given time. So that's the rate. Okay, so the rate is dependent upon those access times. Now, there's typically, you know, computers move a large amount of data on these things, both internal and external transfers, and also multiple devices are trying to access that memory. And if you think about it, if multiple devices are trying to access the same memory, the notion there is one of those devices is going to have to wait. Okay, and if you have a device waiting inside of a computer, your kind of throughput is going to go down with that. There are other external devices that help you with that, namely DMA, which is direct memory access. Essentially allows you to transfer large amounts of information while the processor is doing something else. Very interesting, beyond the scope of this class. So the real slam dunk solution is, as for bumping up the memory bandwidth on this thing, is to increase the clock speed. But what you find out is the memory with shorter access times is more expensive and it eats up more power. Certainly a giant design issue. So these are one of the first computer architecture diagrams we use. This is the first one. It highlights the three main components in computer: I/O, memory, and the brains of the thing, which is the processor. So we pretty quickly broke it down into this. Okay, and if this looks like one memory, but there's two sections in this memory. One is for data and one is for instructions. Okay, so this is actually an important thing that you need to know, is if I'm using one memory for data and instructions, it's referred to as a von Neumann architecture, or also a Princeton architecture. If I'm using separate memories for data and instructions, it's referred to as a Harvard architecture. So this is like super important. Everyone talks about this and everyone knows this. So it's really Harvard versus Princeton, and it's something you just need to convert to memory. I typically have trouble memorizing this because I use a particular architecture and it does one or the other, and I actually forget the terms on this thing. So there are some issues with this, and generally speaking, the Harvard it's considered better for a couple of reasons, and I don't know, better is kind of a stretch, but essentially if I have separate memories, that's going to support memories where the data width is different than the width of the instructions. So RISC-V, it's kind of a fake, but the instructions are 32-bit long, but the data can easily access. The memory can easily access 32 bits. So, in a sense, we have matching bit widths for both the instructions and what we can grab out of memory. Yeah, we can grab other sizes out of the memory, but we can. It works out really efficiently, since we can pass words back and forth between memory and words of 32 bits, and the instructions are 32 bits also. So there are memory bandwidth issues. If we have two memories on this thing, it's going to be less opportunity for two devices needing the same memory at the same time. Additionally, smaller memories are generally cheaper rather than a big memory. In this case, I'm going to use a big memory for both data and instructions. So another issue here is the two different memories better supports pipelining for the same issue that we don't want to be trying to read and write the data at the same time. Pipelining is a form of parallelism that typically advanced architectures use to increase the throughput of the computer in general. So there's two types of computer architectures out there, which is RISC and CISC, and the definitions. This is not the definitions. This is what the acronyms stand for: Reduced Instruction Set Computer and Complex Instruction Set Computer. Okay, these terms are extremely misleading because both types of these architectures are independent of the number of instructions in the instruction set architecture. So computers were historically CISC because RAM was expensive and relatively slow. So what they did was they end up encoding some of the, we'll say, processing and essentially implementing the instructions via microprograms. That was encoded in ROM. So it was faster and cheaper, but as memory in general became cheaper, it became essentially RISC computers became a really viable option on this thing. So it's a classic debate on what's better, is RISC versus CISC. And the thing to note here, if one was slam dunk better than the other, one of them would go away. But they're both CISC and RISC are still around here, and the idea is really the big thing here is the x86 architecture, which is what the PC uses, has historically been a CISC architecture, and for better or worse, and because they always made it backwards compatible, they just kept it as a CISC architecture, and I could say for better or worse because there are some issues associated with that. So yeah, we're using RISC-V. Yeah, clearly it's a RISC architecture. It's right there in the name, but there are some characteristics that go with the RISC architecture. So number one, the instructions are relatively simple. Okay, and you know, and this is you'll see below everything up here. Everything down here is the opposite of everything up here. So keep that in mind. Instruction words in a RISC computer, they're all the same size. You'll find out that in a CISC computer, some instructions are a different length, and they have to do multiple reads of memory to get those instructions out of memory. Generally speaking, the instructions in a RISC computer, they operate the same number of clock cycles, and that they typically have larger register files. I remember the register files holds a bunch of general purpose registers. It's quite interesting. x86 architecture has very, very few instructions in it, and I'm sorry, very few registers in it. And the idea here is they swap data back and forth between memory. They're expected to, because there's so few registers. So they, instead of having a working register, they swap it back and forth between memory. Okay, so in this in RISC architectures, they have very few addressing modes, and this is the way that the trick ways you access memory. We just don't have that many. I think we have one, right? I guess maybe you could call it two, but we have the base address plus the offset. That's it as far as addressing modes go. CISC architectures, they have quite a few addressing modes, and the issue here is the addressing modes require extra hardware. Yeah, they're handy, but they require the extra hardware. So the CISC computers, as you can imagine, they have more simple hardware. That being the case, we can bump the system clock speed up on it, and that doesn't really mean anything, because everyone used to say, I have a really fast system clock, and it doesn't really describe what's going on in the architecture. But generally speaking, what you'll see here is coming up with this thing. We'll switch to this thing. We'll go down the bottom. What you see is in a RISC architecture is the hardware is really simple, and the instructions are really simple. And the hardware is really simple because the instructions are really simple, and the programs they have a lot of instructions, but those instructions execute pretty quickly. In a CISC architecture, you have fewer instructions. The instructions do more, and because they do more, the hardware is more complex. Okay, and then more complex, it's bigger footprint and all that stuff. I think the drawback on the RISC is that only issue is since there's more instructions, instruction memory needs to be larger. So RISC, kind of a couple other differences up here. RISC architectures, they're often referred to as load store architectures because in CISC architectures, you can often read data from memory, crunch it, and write it back all in the same instruction. So we essentially, if it's a load store architecture, they have special instructions that access memory. And you're not going to be able to read, crunch, and write back all in the same instruction. Generally speaking, the RISC architecture has less hardware, requires more instructions. Also, a really important factor here, the RISC architectures support pipelining, which is once again a kind of an advanced computer architecture topic that you'll see later. CPUs. This is kind of an antiquated term because it's central processing unit. When hardware is expensive, everything just one module did all the processing, and as you can imagine these days, there's multiple modules in a computer that you could say does processing. The definitions out there of a CPU are varying, but the most popular one, it's the part of a computer that executes instructions. So I kind of chuckle at that because I think, you know, pretty much the entire hardware architecture is responsible for executing instructions. Typical submodules here: the control unit, data path, which is coming up next, program counter, instruction memory, register files. All these are included in there, but once again, it's kind of memory specific. It's definitions specific. People define it differently, but one thing that's not included in the CPU is the external peripherals, and we don't really have any external peripherals in what we've looked at, but typical microcontrollers will say have a whole host of external peripherals in this. Oftentimes they use CPU. It's a synonym for just computer or microcontroller or processor. The data path. Okay, once again, it has contextual definitions. It's a common word in computer architecture. The simple definition is just the path the data takes. But in the computer definition here, it's coming down here. It's considered the part of the architecture that does the number crunching. So some of the data path modules are considered to be stuff like the ALU and the register file and the muxes assorted that you've seen in the diagram that handle all the selection of operands to the ALU, etc., etc. So questions and answers here. In RISC-V architecture, what is the lowest level of memory and why? Well, for us, it is the register file, and it's the fastest memory compared to. We consider it fast, not in the semiconductor sense, but it's fast in the sense that if I have to get something from memory, if I have to crunch data in memory, I got to load it from memory, put it in the register, crunch it, then write it back, and that's why it's considered faster. The register memory is considered faster. So since the register file is considered lower level memory, what is the main drawback of increasing the register size? So if you can increase the register size, that means having the register file size. That means having more general purpose registers. The idea is we have 32. Since we have 32, we have to address those things, and each of those take 5 bits of address space. So suddenly we have 64 general purpose registers. Suddenly we have 3 extra bits that need to be dedicated to differentiating the various registers, and we not something we really want to do in that thing. Oh yeah, it might be for the computer you designed, but not typically. 32 is considered a doable amount. How can multiple devices accessing a single memory cause memory bandwidth issues? Because what happens is you've got multiple devices accessing it. Sometimes they're going to access at the same time, which means one of the devices is going to have to wait. If you've got a device that's waiting, it's going to drop the throughput of the computer down. It's going to slow the operation of the computer down. Okay, so using a faster memory can solve bandwidth problems. What are the drawbacks? Well, faster memory is more expensive and it takes more power. Okay, if you're working with an embedded system, it's typically run off a battery. Having faster memory is going to cost you. So if I add 100 new instructions to my RISC architecture, can I still refer to it as RISC? Okay. Well, issue is I didn't give you enough information for this problem. It's not a matter of how many instructions there are that decides whether it's RISC or not. It's a matter of the complexity of the instructions. So if all those if I added 100 simple instructions to that RISC architecture, you could argue that it remains a RISC architecture. If I add some complex instructions there, it's going to be considered a CISC architecture. And there are the answers there, and there's the big diagram, and that is it, folks.